Hello everyone, my name is Edward Jones. I'm going to be talking to you today about how we can scale a GaN half-bridge design to any power level that you need for your application in DC-DC converters and in low voltage motor drives. So let's begin with the basics. What is a cool GaN Schottky gate HEMT? This is what I'm going to be talking to you about today. This is Infineon's technology and product line for 100 volt GaN, as well as a number of other voltage classes. GaN, as most of you know, is a wide bandgap semiconductor. It makes a great material to be used in a power transistor. We use this to make a GaN high electron mobility transistor. It's a lateral device, not a MOSFET, and inherently it's depletion mode. So there's a number of normally off approaches on the market. There's cascode devices, there's gate injection transistors. What I'm going to be talking to you about today is a Schottky gate GaN HEMT, which uses a Schottky gate contact to raise the threshold voltage, but at the same time it results in a semi or pseudo insulated gate. So you can, in a lot of ways, treat it like a logic level silicon MOSFET, but it's not one. It does have a different switching behavior, gate driving requirements. With the right design approach, you can achieve extremely fast switching behavior that can be scaled to any power level in your target application without sacrificing in the performance or power density of that design. So let's start with the recommended half-bridge layout. So in this design here, I'm showing you two 100 volt cool GaN Schottky gate HEMTs, each 3 milliohms in a PQFN lead frame package with dual-sided cooling. And next to that, you can see some 1EDN 71X6U drivers. These are TDI ICE drivers, which I'll get into a bit later. On the right, I'm showing you the top copper layer and the first inner layer with an 80 to 100 micron dielectric spacing in between the top and first inner layer. The critical thing here is the geometry, the orientation of the components. I have the 100 volt decoupling capacitors at the north side of the PCB here. And then going south, we see the high side switch, the low side switch, and then some vias, which return in the first inner layer. You can see here in the red lines, and they return completely differential to these green lines. So you're seeing that the high frequency current is fully differential in the power loop, and this actually causes the magnetic field to mostly cancel. And you can achieve with this layout a 400 picohenry power loop, including those capacitors and both switches. Now, completely perpendicular to that, you see the two gate loops. This includes 4 loops total. You have the high side source and sink gate driving loop to turn the high side gate on and off, and the low side source and sink. It's important that these are orthogonal. It's important that they have dedicated return paths on the first inner layer, and this also achieves a very low inductance in the range of hundreds of picohenries. But this is just a single half bridge. How much power can we get out of this half bridge? That depends on your cooling conditions. So the recommended cooling approach here to extract the most power out of a single GaN half bridge is to use dual-sided cooling with a fixed gap approach. You can see here an example where I have a heat sink with the height matched to the surrounding inductors, the area matched to the half bridge. So we're not adding any volume to the design. We're just using the available empty space. We're using an ultra soft compressible thermal interface material pad with a very high conductivity. It's soft, so it doesn't apply undue stress or pressure to the top of the GaN device. And the high conductivity means we can achieve very low thermal resistance. And the integrated standoffs milled into the heatsink allow for a fixed gap without any complicated assembly process. You can use screws, you can use clips to attach it. There's no springs needed. But that only allows us to extract a certain amount of heat. Even with the best cooling approach, we still only have one single 100 volt 3 milliohm GaN switch for each switch position, high side and low side. If we want to go to higher power, you might consider paralleling. A lot of people might be concerned about paralleling GaN, but I can tell you it's actually much easier than you might think. In steady state, there's a very strong positive temperature coefficient that helps to balance steady state drain current between parallel GaN devices. This is because the RDS on is going to increase as any device warms up, and this is going to mean that the current self-balances between parallel devices. Dynamically is a different story. Dynamically, we need to think about the threshold voltage and the transconductance, so just overall the transfer characteristic. What you can see here on the right is that basically compared to silicon, a GaN transistor has nearly zero threshold voltage variation with temperature, so this isn't really a concern. However, the transconductance, the saturation current, is strongly related to temperature in the same way that RDS-on is. This means that dynamically the current is also going to self-balance. In any particular switching transition, the hotter devices are going to carry less of the switching commutation current, and the colder devices are going to carry more of the hard switching burden, and thereby self-balance current and temperature during switching as well. But this leaves one concern, which is the symmetry of the PCB design. We have to make sure that all of the loops are very symmetrical and well matched. Here's one approach of how we can do this in a very small motor drive. This is a 48 volt, 1 kilowatt motor drive with two devices in parallel. You can see it's very, very small. We actually call it the matchbox because it fits nicely inside a standard size matchbox with still space to spare for all the matches. What we do here is we have two paralleled half bridges. I'm not talking about paralleling devices here. We're actually paralleling two half bridges. That being said, we have each gate driver is driving parallel devices. So you have one driver for the two high side, one driver for the two low sides, but each power loop is oriented as parallel half bridges. And you can see here in the green and the red lines that we have completely symmetric source and sink loops for both of the gate driver loops, from the single gate driver to the two high sides, single low side driver to the two low sides, and the power loops are also well matched. Here we're using this fixed gap approach heatsink technique, but in this case we're not even using a heatsink, we're actually just using the enclosure of the motor drive as a heat spreader. Let's take it a step further. Let's look at this design here. This is a motor drive designed for 8 kilowatts with 8 half bridges in parallel. You can see again we have parallel half bridges, not parallel devices, from the perspective of the power loops. That being said, if you go down to the inner loops, the mid-layer 2 and mid-layer 4, we have paralleled gate loops. Each of these gate loops is within about 1 nanohenry, so very low inductance because we're using differential returns, and they're also highly symmetric. So in the green here, we're seeing the low side driver. In the purple, we're seeing the high side driver, and these are routed very carefully in inner layers so that we have the same 1 nanohenry inductance to match the switching dynamics. And the result is, as I showed you before, is a very ultra compact, very thin motor drive that can achieve high power for applications such as e-scooters and high power tools. Here we've just discussed motor drives, and in that case paralleling devices makes the most sense. But what about DC-DC converters? In this case, maybe not. So if we look at a single DC-DC converter stage, like here we have a single phase buck converter is the basis of all of these designs, this single half bridge and a standard half bridge evaluation board. We start with the transistors and the drivers, but this isn't the entirety of the DC-DC converter. We also have to consider the microcontroller. In this case, I'm using a microcontroller that can very easily drive 2 interleaf buck phases, and the controllers themselves can be synchronized to parallel multiple phases in pairs. Then we have to consider the inductors. Here I'm using very new best-in-class inductors from Vishay. They're powder core with a high current capability and 2 different height options. So you can optimize for power density and you can optimize for efficiency depending on your restrictions. And I'm using DCR current sensing with these inductors because Vishay was kind enough to offer binning into tight plus or minus 1% DCR groups, allowing for lossless current sensing. Here I'm showing you 2 examples of this approach. I am scaling these phase pairs into a 2-phase design and a 6-phase design. The same phase pair in each case, scaled really without much limit. You can scale to any power level you want. In these cases, I'm achieving 1600 watts with the 4-phase. I'm achieving 2400 watts with the 6-phase, but the same power density, the same peak efficiency in all cases. So let's get into that. Let's talk about efficiency and power density. In the board that I'm showing you here, I'm achieving a peak efficiency of about 97.3%, 96.7% peak with a 48 volt input, and the power density is 430 watts per square inch in terms of area 1120 watts per cubic inch in terms of volume. This DC-DC converter is mostly positioned for servers, for data centers. And in this case, you have a finite amount of space on the server blade, on the motherboard. In that case, maybe you don't care so much about height. So it might make sense to use the 10 millimeter height inductor, a slightly taller inductor with a higher inductance. We can drop the frequency just a hair from 500 to 300 kilohertz. Now this keeps the same area power density of 430 watts per square inch, but a lower volumetric power density of 850 watts per cubic inch. So it's not perfect for every application, but for servers, this really is not much of a compromise at all if you have the 10 millimeter height available. And as a bonus here, you get about 1% peak efficiency improvement by re-optimizing for a slightly higher volume. And there's an added value of scaling in terms of phases instead of scaling in terms of parallel devices. It allows us to use integrated power stages. Integrated GaN half bridges are not so easy to parallel because they have separate drivers, and paralleling drivers is difficult. You have to deal with propagation delay tolerances. But if you're paralleling phases, then each phase can have a fully integrated power stage like this guy here. This is a 100 volt CoolGaN IPS that we have in development. It's in a 6x9 millimeter package. The entire power stage is included, and that doesn't just mean the two switches. It also doesn't mean the two switches and the driver. It's literally the entire power stage. So it includes the VDD bypass capacitor for the low side driver, the bootstrap circuit, as well as the bootstrap capacitor for the high side driver. It even includes the 100 volt high frequency bypass caps. So in fact, all of the gate driving high frequency loops and the power loop is completely enclosed within this 6x9 millimeters. It allows for much more flexibility in the design of the DC-DC converter because you're only using the top layer of the board and you don't have to worry about optimizing the high frequency loops. There's also a version in development with dual-sided cooling. Use a completely galvanically isolated topside thermal pad for easy heatsink attachment without even using a thermal interface material. So in conclusion, I just want you all to understand that the CoolGaN Schottky Gate HEMT in a half bridge can be scaled to any power level that you need to address. Different applications may require different approaches to scaling different power levels. You might want to parallel devices, especially in applications like motor drives. But then when you have to think about other components like controllers and especially magnetics, it may make more sense to optimize for power density and efficiency by interleaving parallel phases. We have at Infineon a complementary ecosystem of drivers and controllers. We have partners that have really terrific magnetics available to support these designs. And to demonstrate these techniques, I have shown you 4 different designs, 2 motor drives scaled for 1 kilowatt and 8 kilowatts, and 2 DC-DC converters scaled for 1.6 and 2.4 kilowatts respectively. Thank you very much for your time and have a nice day.